Oh. Kara?
Hello.
Thank you. Good seeing you. I'm sorry I had difficulty logging in tonight.
Oh, that's okay. It's computer issues. I figured maybe you were having internet issues, so I was just waiting for an email to pop up at some point.
No, actually there should have been two. That's the problem. I think I get a lot of people on the other one. Hold on one second. I got a phone call.
Yeah, go ahead.
Yeah, my wife answered. Eva, 1 second.
Madison's in your waiting room. Hang on.
Madison is not in my waiting room.
Oh, she says she's not.
It might be in the first one.
Does it say in the waiting room?
Yep, I got a waiting room.
Maybe
Madison, you're not there. Madison? Oh. Madison, did you get the first or the second email? Try the second one. Okay. Okay. Madison, go back into the email. There should be another one. Okay. Yeah, I'm sorry. I had trouble logging in. All right. No, you're good. So just get in here and I'll tap dance until you get here. Okay. All right. Bye. And she's in. Okay, I got Kara. Are you still hearing me, Kara?
Yes.
All right, the other part, Madison, are you hearing me?
I made it.
Sorry, I am sorry about that, but I had trouble logging in for some reason tonight. I couldn't get into the St. Pete site for Zoom. So I accidentally got into I have to have two sites because of HCC. And because of that, there was something screwed up. Can you guys hold on a second while I get into my try and get another email out to people? It's 1 second. Email. Be there in a second. It won't take us that long to do this tonight. If you can't get on, all right. How are we doing, guys? We doing okay?
Ready for the semester to be over.
Oh,
yes.
You and me both. It's not been a banner 4 months for me either. Trust me on that. So I believe me, I know where you're coming from. All right. It's, guess what? 2 more. Okay. 2 more, this one and next week. And we're done. Well, we're not quite done. We have that little matter of the final. Okay. But all intents and purposes, all the experiments are done. All we're going to do next week is kind of a workshop for Lewis Dot and for Vesper. Okay. So that's all that's left, guys. So last week's experiment easy to do? Absolutely finest kind. It's even better. It's easy for me to grade, so that's even better for me. Come on, Veronica, smile a little bit. Thank you. All right, let's get this over with, okay? Is that that a choice? Now it's not allowing me to share screen. Nope, I don't want that. Don't do that. That's the one I want. Everybody's saying the screen that says vapor pressure. Okay, I'm not hearing anybody. Is there some reason why I'm not hearing anybody?
We see.
All right. Thank you. Okay, guys, we live in Florida. We know about vapor pressure. We know the ability for water to come out of its liquid stage and to surround us with all this wonderful swelteringness called humidity. We know about it, okay? Now, water vapor's pressure, the pressure that water has, it emits to the air, is dependent upon two different variables. It's dependent upon the temperature of the air and the pressure of the atmosphere. These are the two things that it is dependent on. It's also dependent on the individual heat of vaporization. Okay, the heat of vaporization is unique to each gas, to each liquid that's getting evaporated. But other than that, we depend upon the pressure of the atmosphere and we depend upon the temperature. Now, do you know what happens when water boils? What is actually happening when water boils? I know you guys actually have lives. You're not like me. You don't sit there and stare at the stove waiting for your pasta water to boil. Now, this is my life, just waiting for water to boil, right? But what is happening? If you do sit there and watch water boil, what you're going to find the first couple minutes, you're going to have what I call the false boil. You know, you get all these little bubbles that are there and you're thinking, yeah, it's about to boil, yeah. But no, it lasts forever until it boils. What's happening? Those little bubbles you're seeing, that's the gases. The gases that are dissolved in the water. We got to get rid of all those first. And all this is taking energy. It takes energy to take those gases and remove them from the water and allow them to collect and allow them to float up and go away. That all takes energy. And we got to put more energy in. And we got to keep on putting more energy in. And if we look at the bubbles start at the bottom and they burst. Start at the bottom, go a little higher, burst. Start at the bottom, burst. And it isn't until that bubble has enough energy to escape from the intermolecular forces of the water to escape those and reach the surface and explode out. That's what causes something to boil. And the amazing thing, when we are reached the boiling point, that is the temperature at which the liquid's vapor pressure equals the vapor pressure of the surrounding atmosphere. So that's basically what we're dealing with. Does everybody kind of understand that little synopsis, guys? Are we good?
Yeah, pretty clear.
Okay.
Monica said she was leaving and coming back, so she might be in the wait room.
She's back.
Okay.
At least I thought she was back. She was back for a second anyway. She's back.
Yeah.
Okay. All right. So, yeah. So basically, what we're doing when we're boiling water, when we're boiling anything, we're increasing the vapor pressure to the point where the vapor pressure equals the outside temperature or the outside pressure. So if I tell you something boils at 100 degrees, right then you know what its vapor pressure is, because at its vapor pressure, its pressure equals atmospheric pressure. Now, the other thing you have to realize about boiling point, what boiling point is actually, we have these intermolecular forces. Does anybody have Dr. Musgrave, and are you on intermolecular forces yet?
Yes.
All right. The rest of you are just going to have to bear with me. I'm going to keep this fairly general because of the fact that most people haven't had it. Just suffice to say, if you have a greater intermolecular force, intermolecular forces hold one water molecule to another. And if you have a greater force, it's going to take more energy to separate them, because we got to separate the molecules to go from a liquid, which has things that flow, to a gas, which we have things moving around rapidly. So we have to deal with breaking those intermolecular forces to evaporate this stuff. Now, when we're breaking the intermolecular forces, we're not adding any more temperature, because when all the energy that we're putting in there is going to breaking these intermolecular forces. So we don't have any extra energy to raise the temperature. So when we're at the boiling point, the temperature stays constant. And it's going to stay constant until we have taken all of the liquid and made it into a gas. Once it's a gas, that temperature can rise again. Does this make sense to you guys?
Yes.
Do I hear an amen?
Yes.
So therefore, guys, if we put a thermometer above a boiling liquid, we're not going to see that temperature rise in that thermometer. If you look at it, again, this is me who has no light. If you look at a thermometer while this stuff is boiling, what you're going to see is the gaseous bubbles condense on the upper edges of the thermometer. They're going to condense, then they're going to collect. Then when it gets heavy enough, it's going to float down, and at the very end of the thermometer, it's going to drip. Has anybody ever seen that happen?
Yes.
Then you don't have a life either.
Thanks.
All right. So in order for this kind of stuff to happen, the temperature has to be high enough for the pressure of the vapor to equal atmospheric pressure. All right. So that brings us to an equation. The equation is called the Claussius-Clapeyon equation. And I've told you before, what chemists do is they take an original relationship, an original equation, and they will manipulate that equation around so that they can get two things they can measure to use them to make a graph that has a slope that will allow us to get something we can't measure. So the Claussius-Clapeyon, what happened in that equation is they basically took the log of both sides of the equation, and that developed into this eventual equation, which we have the ln of the vapor pressure of the gas is equal to negative the heat of vaporization of that gas divided by RT plus the ln of some constant that's also related to the gas. So P is the vapor pressure at a specific temperature. T is that temperature. And delta H vap is the enthalpy of the vapor at that particular time. Something you need to note here. I believe this is the first time you have been exposed to this. R does not equal 0.08206 because when it equals 0.08206, the label for R is liter atmospheres per degree Kelvin mole. We've changed the value for R. R now reads joules per mole Kelvin. So if it's a different label, the number is going to be different. The value of R is 8.314 joules per mole times Kelvin. Now, the other thing you have to note about this particular equation is that enthalpies are given in kilojoules per mole. So our H is in kilojoules, our R is in joules. We have to convert one or the other. All right, if we look at this, in some convoluted chemist's mind, this constitutes the equation of a line, and it really does. Because if we plot the ln of our vapor pressure versus the ln of 1 over T, this is my y-axis, this is my x-axis. If I plot the ln of P versus 1 over T, I get a slope. And that slope is equal to negative heat of vaporization divided by R. Is this kind of making sense to you guys?
Yes.
The lab itself is going to be a breeze. All right. If we measure 2 points, if we measure 2 temperatures and 2 vapor pressures, then by manipulating the original formula, by manipulating this formula, we can develop a combination formula or the Claussius-Clapeyon 2-point formula. And that formula is ln of the vapor pressure at some point, at some condition 2, divided by the vapor pressure at some condition 1 is equal to the change in the delta H vape divided by R times 1 over the temperature that's associated with the pressure on top minus 1 over the second temperature, which is associated with the vapor pressure on the bottom. Are we good with this? Are we good with this?
We are good as gold.
All right, now I want to confuse you. I can change this entire equation around, and it still means the same thing. If I put the ln of P1 over P2 is equal to minus delta H over R times 1 over T1 minus 1 over T2. Do you understand that? That is just a mathematical manipulation. Do you buy that?
Yes. Yes.
All right, I'm gonna further confuse you. If I take the ln and put P1 over P2, that is equal to, instead of this being a minus sign, this is a plus sign, plus delta H over R times the parentheses 1 over T2 minus 1 over T1. I said that to you. I know it sounds confusing as hell. These are only mathematical manipulations of this equation. The only reason I'm even pointing it out to you is the fact that you are going to have different textbooks that display this equation differently. All I want you to do is memorize it in one way. Write it down one way each and every time, and you're not going to have a problem ever, okay? If you just put P2 over P1 and the T1 minus T2 minus T1 and keep a negative sign in there, you'll be okay. Now, the first thing we're going to do, we're going to shove some liquid into a test tube. It doesn't matter how much. Just shove some of the test tube, some of the liquid in a test tube. And we're going to fit a thermometer into a rubber cork. We're going to put this into a water bath and we're going to heat it slowly. We don't want to heat it rapidly because we create a cannon. And God knows we don't need any cannons around. What we're going to do is we're going to observe. We're going to watch the thermometer. The temperature is going to continue to go up. Then the thermometer is going to stay at a steady temperature. It's at a steady temperature because at that point, all the energy is going into breaking intermolecular bonds, and we're looking to turn the liquid into a gas at that point. Until it's all gaseous, the temperature will not go up. So when we have a steady temperature like that, we are at the boiling point. Exact boiling points are hard to detect. And generally speaking, we record them as a range. In our particular case, ours boiled from the range of 61 to 69 Celsius. That's the first step to what we're doing today. Now, you're going to go into your lab manual, page 117. You're going to find a chart there. In there, you're going to find a boiling point. With that boiling point, you're going to find the name of the compound and its subsequent delta H. So we have a temperature. What you're going to do is you're going to average the range of your boiling point. You're going to have a delta H, and you're going to have an R. All right? Now, we know something else. We also know the pressure that methanol exerts at 65 degrees Celsius, because that is where methanol boils at. We've been asked to determine the vapor pressure at 295. Remember, our average boiling point was 65 degrees. We know when something's boiling, the atmospheric pressure is equal to the vapor pressure. So at 65, we know the vapor pressure is 760. What you're asked to do is you're asked to determine the vapor pressure at 295. What you're going to do is you're going to use the Claussius Clapeyon 2-point formula. You want to know vapor pressure at 295. So we don't know what P2 is. We know P1 is 760. We looked up our delta H. It was 35.3 kilojoules per mole. So I changed that because it's kilojoules and R's and joules. I changed the kilojoules to joules by multiplying it by 1,000. So my delta H is now gone from 35.3 to 35,300 joules. I divide that by my R, which is 8.314, and I multiply that by 1 over 295, which is the temperature which corresponds to P2. That's the one we want to find out what the vapor pressure is. That's subtracted by 1 over the boiling point temperature, which is the atmospheric at 760. All right. So we do the math out on the right side and we get negative 1.83. So the ln of P2 over 760 is equal to a negative 1.83. Now, something I see constantly. When you get to this point in the mathematical calculation, what you guys have a tendency to do is you have a tendency to multiply the negative 1.83 by 760. You can't do that because it's the ln of x over 760 that's equal to negative 1.83. So when we reach this stage, we have to raise both sides to e to the power. E meaning the natural log. E meaning the 2.73 such and such and such and such a thing. So if I raise e to the ln, anytime you raise e to the ln is the number 1. So the ln goes away. So I now have on the left side P2 over 760. Now that's equal to e raised to the negative 183 power. E raised to the negative 183 is 0.162. So P2 over 760 is equal to 0.162. 0.162 times 760 is equal to 123. That is the vapor pressure at P2. Any questions about the formula or about the math, ladies and gentlemen? God, you guys want to get home and you want to eat something. Okay? Are we good with this? This is the first half of this experiment.
We're good.
Second half. Okay, on page 120 of your manual, you're going to find data of vapor pressure and temperature. What you have to do with those two columns, the pressure you have to convert to LNP. The temperature you have to convert to 1 over T. Then, guys, you are going to make a graph. LNP is the y-axis. 1 over T is the x-axis. You're going to make a graph, and that you're going to, out that graph, you're going to create the equation of a line. So the equation of my line here is y is equal to 4636.7x plus b. Okay? Now, you have to realize that your slope is also by the Claussius Clapeyon. The slope is equal to negative delta H divided by R. So if I take my slope and I multiply that by R, that will give me delta H. All right? Then I get, that's going to be a fairly large number, is equal to delta H. What I need to do is I need to convert joules to kilojoules to put it in the right format for heat of vaporization. Do I have any questions, guys?
What do you say we have to convert the vapor pressure for?
Okay. Veronica, where are you asking the question? For my part A, where I was doing the two-point Clausius Clapeyon, or part B, where we're doing the graph?
We were doing the graph.
Okay. Now, all right, do you see this formula, Veronica?
Yes.
If this is y, if LNP is y, and 1 over t is x, then my slope is going to be this whole thing, a negative delta H over R. Are we good with that?
Yes.
All right. So if I know what my slope is, and my slope happens to be a negative 4636, I'm going to multiply that by a negative 8314, and that gives me 38,500. That's equal to my delta H of vaporization. Okay? My delta H of vaporization is equal to 38,500 joules. By convention, we put heats of vaporization, all heats of enthalpy, we put them in terms of kilojoules per mole. Does that make sense, Veronica?
Yes.
So once you get the big long number, you got to convert that to kilojoules per mole.
Okay.
Any other questions, guys? Okay, I'm going to stop share. I'm going to get out of my thing, and I'm going to go get into my I'm going to check a thing to make sure that I have loaded the PowerPoint in here. If I haven't, I will do that right now. Doesn't look like it. As a matter of fact, looks like there's a couple missing. Anybody remember what we've done besides TLC since Beer's Law? Somebody real quick, if you could. Oh, never mind. Never mind. What? Oh, that's right. That's a crappy thing. All right. Open. Oh, crap. There we go. Now it should go in there. Good. Open. Good. All right. I know the TLC needs to go in there as well. I think the rest of the stuff is in there. If I could be, calorimetry is in there. Yeah. I think they're all in there now. Sorry, I missed the thin layer chromatography for some reason. All right, so the PowerPoint is in there if you should need to look at it. Another thing, Dr. Musgrave has put in there a video of the calculation. So if you click on that, that's going to be a video on how to do the Claussius Clapeyon calculation. If you don't like my explanation, God bless you. I'm not perfect. He might be able to explain it where you can understand it better. All right. Our results section. Again, this is not going to be long and involved, other than it's going to be tedious doing all of the calculation changeovers. Okay, don't worry about the unknown number. You get a free 5 points. Boiling point that's listed in the data, student data. Okay, if a range was recorded, take the range and make it into the average. Then basically, you got to tell me what the atmospheric pressure is at boiling. Determine, basically, you're going to use the text box to use the Claussius Clapeyon 2-point to determine what the pressure is at 295. You're going to need to put the graph in from part 2. What you're going to have to do, it's a free 25 points, guys. All you're going to have to do here is show the equation of a line. You're going to do that in Excel. So you're going to do it in Excel, and you're going to show the equation of the line here. You get all 25 points. Then, you're going to, okay, the equation, let me back up. The A is going to be the equation of your line. B is going to be the calculation. You're going to know what the slope is from the equation of the line. You're going to have to multiply the slope by negative r to determine what delta H is. So that's all you're going to do here. That's the entire lab. Questions about the results section. Okay, we'll get out of here. All right, go back into course content. By the way, are you bored by me going through these? I need to know for next year. Is this, my going through this, is that a good thing for you guys? Or are you just bored and you just want to leave at this point?
I personally think it helps me.
Very helpful.
Yeah.
Okay. I'm just, if it's not helping you, then there's no sense. Somebody needed to tell me long ago that I was boring the snot out of you. Post lab. And my guess is you're going to have a couple questions on the Claussius Clapeyon equation. Okay. Ugh. No, it's nothing bad. It's easy. Okay. You got 44 is the known value of your heat of vaporization. 44.48 is experimentally determined. Determine the percent error. They give you the formula up there even. You have the heat of vaporization of 32.19. Normal boiling point is 88. Remember, at normal boiling point, the pressure is 760. What is the vapor pressure and torr of this liquid at 25 degrees Celsius? 2-point Claussius Clapeyon. Questions about that one? All right. They switch it on you. Okay. They're asking you what the normal boiling point is. They give you the vapor pressure. The vapor pressure at this temperature is 99 torr. They ask you what the normal boiling point temperature is. You know the atmospheric pressure at boiling is 760. So you have two pressures, one temperature. Solve for the other temperature. Anything else here, guys? Yeah. Exit preview. That's going to shove me back there. Now, last thing, and I will get out of here. Okay. Lab manual. You're going to have to go to the lab manual to get the information for the graph. Oh, crap. No, do not do this to me. Huh? Are you guys still saying this? Are you still with me at least?
We're here.
All
Yes.
right.
Yeah,
No, are you
yeah.
still with the screen?
Oh, yeah.
Oh, yeah, I got to do this. All right. Did anybody write me? That's telling me somebody sent me something. Did anybody send me anything that I need to respond to?
Now that I remember of, I usually send you emails, but I don't remember.
No, no, okay. Hopefully this is right. Yay. Finally. Okay. All right, we're going down here. We're going to go to the very back end of this. All right. Do you remember when I was telling you that there was a chart in the laboratory where you look at the boiling point and that will tell you the substance and the heat of vaporization? You're going to need that for the 2 point because you need this to help solve for the second pressure, okay? This is where you find it. Your unknown is going to be one of these 6, and you're going to know it by the boiling point. The other thing you're going to need in here is this table. This table gives you temperature and vapor pressure. You got to change all of these into ln of P. You got to change all of these into 1 over T. Then you're going to put this into Excel and plot it. Unless, of course, you want to be real adventuresome and do it by hand. Any
Is
questions?
this in the manual?
This is in the manual, yes.
So, the way that we convert ln, the vapor pressure to lnP, is it?
Okay. Veronica?
Yes.
All right. You have a calculator with you. Chase, you ask me questions and you're not even prepared.
Yes, I have a calculator here.
All right. Look at a calculator. Do you have an LN button somewhere in that calculator? If not, take it and throw it in the toilet.
Yes.
All right. Now, what I want you to do is I want you to hit the key. LN, hit that.
Okay.
Type in 9.2. Enter.
Wait. I gotta press another button.
If your calculator does something funky, I can't help you with it. All right.
Okay.
You should be able to just, by the way, guys, I have nothing more to tell you other than one more thing. All right. Next week, we are doing Lewis dots and Vesper. Traditionally, I spend about an hour and a half talking about it. I'm going to look at this as a workshop, though. All right? I'm looking at this as a kind of workshop where you can ask me questions about things. I will have something prepared, but it's going to be kind of a workshop. And we're going to stay on as long as you want me. If you tell me at 7:01, Mr. Popovich, I don't need you, that's fine. Okay, Veronica, you got it yet?
No, I have the log. I don't have the, I see the ln now. Okay. It's just it's old. It doesn't have the letters anymore. So I gotta click which one it is. 9.2, you said?
LN 9.2. Enter.
2.21.
Let me see. 2.21. Okay. That's all you have to do.
Oh, okay.
All right. Now for the temperature, all you got to do is take 1 divided by 283. That will be what K minus 1 is.
Okay.
All right.
All right.
Is anybody left? I see 7 people left.
I have a few questions.
Okay, Madison, I'm here.
Well, my first one was on the pre-lab. The one question that was you had to basically manipulate the equation to solve for B. Could you just show what the answer is? Because I still don't get how to do that.
Okay. Maybe. Sometimes they throw, it's amazing. You know, you want to know how to completely fluster a chemistry professor? Ask him a problem that another chemistry professor has made. Because like we're sitting there thinking, I should know that. I should know this. So every now and again, you're going to see something. You're going to see a gleam in his eye. And that's where, is this where I have to bullshit the person? I don't do that. I'll tell you flat out, I don't know. And what will happen is I'll research it and come back for you, I promise. Where the hell is it? This it?
Yeah, that's it.
Okay. I'm going to have to get back in there because I don't want to mess with it.
It's right there, the first one. Yeah.
No. Okay. It's not a big deal. All right. Which question is it?
We had to manipulate the equation to solve for like B. It was like ln of A over B, and you had to solve for B. Or manipulate the equation. Yeah, manipulate it to solve for B.
All right.
It was number 3.
Is this it?
Yeah, that's it.
Okay. I'm looking at it without looking at the answers. Okay. It should be E raised to the Z power divided by B. That should be your correct answer. Okay, Madison?
Got it.
All right. What you have to do, this is where, remember when I was telling you that one part where you had to be careful about the mathematical manipulation?
Yeah.
When you raise E to a power, all right, E raised to a power. Are you seeing that? No, I'm sorry.
I see.
I'm sorry. I'm getting tired. Madison's my third class of the day. I'm starting to get tired here. let me rephrase it, all right? If you have ln and you have a number there, okay? If you want to get what that number is, you have to raise e to the ln power. E to the ln is equal to 1. All right, I'm going to stop share for a second. And hopefully I'm going to be able to get my new slide. Okay. All right, you have ln of x is equal to 44. Okay, isn't that the problem they have, Madison?
Yes.
All right, to get rid of ln's, what you have to realize is that e raised to the ln of x damn it, it always does that. Okay, this is how you get rid of ln's or logs. Same thing. To get rid of log, if I have a log of x is equal to 3. Okay? This means I have to take 10 raised to the log of x is equal to 3. Does that make sense to you, Madison?
Yes.
So basically, if I have 10 raised to the log, then to solve for this, 10 raised to the log is equal to 1. Okay, Madison?
Okay.
So e raised to the ln of x, I'm sorry, 10 raised to a power is equal to 1. E raised to the ln is equal to 1. So e to the ln of x is going to be equal to x. Does that make sense? Whatever the log is, whatever the number after the log is, to solve for that, you have to raise, if it's an ln, you have to raise the e to the power. So if I'm solving this problem, I take e raised to the ln x is equal to 44. I'm sorry, excuse me, is equal to e raised to the 44th. Okay? All right. Did you see what I did, Madison?
Are you sharing your screen? I meant to ask you.
Oh, apparently not. Here. Sorry. All right. If I have a problem, ln of x is equal to 44. Since e raised to the ln is equal to 1, it's going to go away. So e raised to the ln of x is just going to be equal to x. I can then solve this by saying, taking e and raising it to the 44th power. Does that make sense, Madison?
It does.
All right, just the same way. If you have logs, The log of x is equal to 3. You got to take this, both sides. I've got to take 10 and raise it to the log of x power. If I do it on the left side, I have to do it on the right, so that my value of x is going to be then equal to 10 raised to the third power, or 1,000. Does that make sense to you, Madison?
Yeah, the manipulations make sense.
Okay, so that's what happens. In the thing where you were they showed to you, they said the log of, and he's doing this to try and prevent you from doing a calculation error that is very, very typical. Okay? This is the way not to do this. The way not to do this is to do ln of A is equal to Z times B. No. The way you do this is ln. I'm sorry, you raise E raised to the ln of A divided by B is equal to E raised to the Z power. All right? And I realize this doesn't look pretty, so I'll try and make it look pretty. Ah. Okay. Now you have to realize that E raised to the ln power is equal to 1. So I've got A divided by B is equal to E raised to the Z power. If I want to solve for A is equal to E raised to the Z power times B. And I may have gotten it wrong when I looked at the thing. I was looking at it real quickly. Madison, does that make sense to you?
It makes sense.
Geez, I got 6 other people here that are interested in logs.
It's complicated and boring, but it makes sense.
It's complicated and boring. And this is something, can I ask a silly question? How many of you have been through second year algebra?
Not for many years.
Not me.
Okay. Now, Kara, you're going to have to get used to working with logs again. Okay? Because
I know.
They are going to come up in Chem 2 quite prevalently.
Oh, that's okay. I have to take calculus, so that's okay. I'm gonna have to learn it, whether I like it or not.
There's a guy, I forgot what his name is. There's a guy at the tutoring center in Gibbs. By the way, I may be at the tutoring center. I got approval from the person to get 5 hours at Gibbs campus, at the Gibbs campus. So, woohoo. 5 hours, guys. Chemistry in the summer. In any case, there's a guy there that's very, very good. It's a little Oriental man. Wonderful, wonderful teacher. People that go there love him. Okay? Anything else, guys?
Last question. Were you able to look over the final? Were you going to discuss that next week? Question mark.
I'll discuss it next week, okay? Madison, it's your job to email me beforehand. You didn't
Okay.
email me, did you?
I did actually.
Did?
You have to go back and check your email.
Sorry. Deny. You know, it's one of the best scenes I've ever seen is in the movie Everything You Ever Wanted to Know About Sex But Was Afraid to Ask. Woody Allen plays this guy who's having an affair. He actually gets caught in bed with another woman. And what happens is he keeps on denying. And as he's denying, he's cleaning everything up. So that by the time he gets done, everything looks the way it should have been. And the woman kind of like scratches her head like, did that really happen? So when in doubt, deny until you get caught. Then crumple like a cheap cracker.
Good to know.
Madison, I will try and get it. If I don't, what I'll do is I'll make it a point to look at it.
Okay.
Oh, hell with that.
No problem.
Stop share. Share screen. Okay. What I will do is I will look at it with you. But